Okay, we now start to take a look at examples involving angular momentum. Let's immediately take a look at the first problem. Please copy it down into your notes. Two skaters, each of mass 50 kilograms, approach each other along parallel paths separated by 3 meters. Each skater moves at 10 meters per second with respect to the ice, which is horizontal and frictionless. One of the skaters is holding onto a pole of negligible mass. When that skater passes the other skater grabs a hold of the pole, and then what we're asked to describe is the subsequent motion. When asked to describe the subsequent motion in a problem such as this, we're essentially looking for two things. What is the translational and rotational motion of the system after, in this case, the collision? Now, this is a collision. Specifically, it's a perfectly inelastic collision because the two objects will stick together after the collision. Because this is all occurring on a horizontal frictionless surface, this then means that the sum of the external forces acting on the system is zero. Therefore, the linear momentum is conserved, but also the sum of the external torques is equal to zero. This then means that the angular momentum of the system is conserved. So let's begin to draw this out in the following way. So we have the two skaters here of the same mass approaching each other along parallel paths, but they're separated by a distance of 3 meters. The speed of each skater is 10 meters per second. So we have, for example, the first skater like so, mass m equal to 50 kilograms, moving in this direction like so with velocity v equal to positive 10 meters per second. Okay, and then right here along this path, parallel to the other skater, is this skater, also of mass 50 kilograms, moving in the opposite direction, however, with a velocity of negative 10 meters per second. The two skaters are separated by a distance here we'll refer to as d, that's given to us as 3 meters. Now, as I said, both linear momentum and angular momentum are going to be conserved in this problem. So let's examine what happens, say, the instant prior to the collision and the instant after the collision. Let's draw that out. So here's the instant prior to the collision. Okay, so the instant prior to the collision, the situation looks like this. So here's the skater at the top like so, moving in this direction with velocity v. And then here's the skater below, moving in this direction like so, with the same velocity v, but just in the opposite direction, same speed that is. Okay, now right here is going to be the center of mass. What we're going to do is set up a linear momentum conservation expression to describe the velocity of the center of mass the instant after the collision. So actually what I should do, quite frankly, is not draw this here as of yet, but instead draw it over here like so. So now this will be the instant after the collision. Okay, so the instant after the collision, here are the two skaters, like so, M and M. Right here is going to be the center of mass. Because the masses of the skaters are the same, by the way, obviously the center of mass is halfway in between them. And then after the collision, there will be a velocity to the center of mass that's unknown. That's going to be describing the translation. But then, because the two people are holding onto a stick of negligible mass, there's also going to be a rotation. So let me now go ahead and draw on the stick like so, as this purple line. And then therefore, if the objects are approaching each other like so and they grab a hold of each other, then they're going to start rotating like this in a clockwise manner. We'll show this specifically with all the directions associated with the angular momentum vectors as we proceed. So there's going to be an omega, like so. That quantity is also unknown. So when you get a problem like this that says describe the subsequent motion, it's basically looking for two things, the translation and the rotation. Okay, now with respect to the translation, as I said earlier, this is a perfectly inelastic collision. So then therefore, let's say that the initial momentum of the system, P naught, is equal to the final momentum of the system, P final. So let's just go ahead and write down each side of the expression here. First of all, the initial momentum. So if we go back up to the top board, for example, or to this board here, the initial momentum of the system is going to be for the top skater, mv, plus then for the bottom skater, m times negative v. Once again, the speeds are the same, but the bottom skater is moving in the opposite direction. This will then equal the total momentum of the system after the collision, which is going to be 2m multiplied by the velocity of the center of mass. Pretty obviously, however, here on the left-hand side of the expression, the total initial momentum of the system is equal to 0. Therefore, the velocity of the center of mass after the collision is going to be equal to 0. Because the velocity of the center of mass after the collision is 0, and more specifically, because there is no external force exerted upon the system, this then means that the rotation is going to be about the center of mass. If the rotation was not about the center of mass, then the center of mass would be doing something like this, which would then mean that there would be an external force exerted on the system, but there isn't. This is all taking place on a horizontal frictionless surface. Therefore, the rotation must be about the center of mass for that reason. So now let's go ahead and describe the rotation here. That is, let's calculate omega, and we'll do so by setting up our angular momentum conservation expression. Okay, so now conservation of angular momentum. Okay, so right over here with this diagram, for point particles, the two skaters, let's go ahead and do a little bit of R cross P for each to find the initial angular momentum of each object. And we'll add those together to get the total amount of the system before the collision. We'll refer to that total as L0 in just a few moments. Well, let's take a look at the top skater first. Right here is the moment arm that is from the center of mass, which the rotation is about, to this point right here where the skater is located. This right here is equal to 1/2 of the distance d. So then therefore for the top skater, we've got our moment arm d over 2, like so. And then here's the linear momentum vector of that skater, mv. The two vectors are separated by 90 degrees. And now we'll go r cross p using right-hand rule. R cross p looks like this into the board. We're going to define that as the positive direction. Looking ahead, notice the direction of my fingers here in my right hand are curling like so clockwise. This then means that the omega vector will point into the board as well, such that we have a clockwise rotation. Okay, so call this angular momentum positive, as I said. The angular momentum vector here is going to be, in terms of its magnitude, d over 2 times mv and then times the sine of 90 degrees. Sine of 90 degrees is 1. So then therefore the initial angular momentum of this object, we'll call it L1 to give it a name, is mv d over 2. Okay, do the same thing for the bottom skater. Right here is that guy's right here is this guy's moment arm vector. So this right here is d over 2. Lost my train of thought for a moment. Okay, right here is its linear momentum vector, like so, mv. And then right here is once again a right angle between the two. Okay, do r cross p to get this angular momentum, we'll call it L2. Watch this. R cross p like so is into the board as well. That's a positive value. So this L2 here is going to be r times p. So it's going to be mv d over 2. Once again, we consider it to be positive. Add the two together to get the total initial angular momentum of the system prior to the collision. We'll call that L0. So that's L1 plus L2. Add the two together, and you just end up with mvd. Okay, and then after the collision. After the collision, what we have here essentially are two point particles, that are rotating about the center of mass like so. What we'll do is we'll calculate the final angular momentum as an I omega. So we'll call this L. And then what we want to describe is the omega, that is the angular velocity of the system, describing its rotation after the collision. So how do I write the rotational inertia I? Well, it's just the sum of mr squareds for point particles. So then therefore for the top particle right here, here's the r, which is equal to d over 2. We square that. And then add that to this point particle right here, where once again, its value of r is d over 2. Like so. So this right here is a d squared over 4. This is a d squared over 4. Add them together to get 2d squared over 4, which is 1/2 d squared. So then therefore I end up with m times 1/2 d squared when I add everything together. Okay, now let's go ahead and multiply that by omega now to get the final angular momentum. Like so. And now what we do is we set the two angular momentum here and here equal to each other, and we then solve for omega. All right, so let me go ahead and do that. That finishes the example then. All right, so I have right here mvd, and that then equals on the other side of the expression, md squared over 2 times omega. Okay, we can cancel out the mass m. We can also cancel out a d here and here, and then we just solve for omega. So omega is going to be 2v over d. Like so. So this is going to be 2 times 10 for 20 and then divided by 3 meters. Let's go ahead and get that as a decimal. Hang on, I need to get my calculator. All right, so 20 over 3, and that comes out to be 6.67 radians per second. And once again, it's a clockwise rotation. We end up then with the angular velocity vector into the board, same direction as the angular momentum vector, okay? Okay, now in this example here, we set up a situation where we had momentum and angular momentum both being conserved. Let's take a look at a situation where those quantities are not conserved. This is a problem involving what is called the sweet spot, which occurs in some sports. So let me go ahead and erase the board. And then I'll move my file to the next example. Okay, so as I'm erasing here, I mentioned the term sweet spot. For those of you that are baseball fans, you may be familiar with this concept. The sweet spot is kind of like that perfect spot on the bat where when the bat strikes the ball almost seems to fly off the ball, and ultimately if you do hit the ball in the sweet spot, then the odds of you hitting a home run, for example, are actually quite good. So what exactly is meant by the sweet spot? The sweet spot, by the way, also applies in situations involving, say, tennis with a tennis racket, or say in golf with a golf club. Let me go ahead and turn this into an example. Let me move my file. Okay, we'll be doing this problem just in terms of variables, but it says at what distance from a fixed pivot at one end of a uniform stick of mass m and length L should the stick be struck such that no reaction force occurs at the pivot. This is known as the sweet spot on a baseball bat. It's also applicable to golf and tennis. So here's what I mean. Let's say that I have my baseball bat like so, and then right here is a baseball. And then let's say, for example, that I'm holding the bat like this, and I then have the baseball collide with the bat like so. Okay, now when the ball collides with the bat is going to butt up against my hand like this. This is the reaction force that is being described in the problem. However, if the ball strikes the bat at a specific location, then the amount of reaction force that occurs in my hand is equal to 0. In other words, I'm able to deliver all of the energy of my swing, for example, into the collision between the bat and the baseball, giving the baseball the greatest speed off the bat. This will occur at a specific distance from the pivot, which is roughly halfway in between, if you will, this big butt end of the bat. That's what's known as the sweet spot. So for those of you that have swung a baseball bat and have collided it with a baseball, and you know that you've hit the ball really well, the reason for that is because you're not feeling any reaction force in your hand at the location of the pivot. This will only occur at a specific distance along the bat. Okay, now let me move this off to the side. Like so. And then what I'm going to do is I'm going to take this horizontal situation that you saw me demonstrate, but I'm going to draw it like this. Okay, so here's the baseball bat. Okay, it's not vertical. I'm just holding it horizontally. And right here is where my hand is. Right here is the pivot. The baseball bat has a mass M and a length L associated with it. It's a uniform stick. Okay, and then right here is going to be the baseball striking the bat like so. Right here is going to be the center of mass. And then right here, exerted upon the baseball bat, is the force that the ball exerts upon it. We're going to refer to that as F. Okay, now when the ball hits the bat then butts up against my hand in this direction. So if I'm holding on to it here, there's a force on my hand in that direction. Therefore, by Newton's third law, my hand pushes back on the bat in this direction, like so. This right here is the reaction force. We're going to refer to it as capital R. Okay, what we're asked to calculate is this. What is this distance here, we'll call it x, such that the reaction force is equal to 0. That's what's being asked for in the problem. This point right here, then, therefore, would be the sweet spot. So let's find x such that R is equal to 0. That's what the question is asking us. Okay, now this is once again a collision. However, linear momentum and angular momentum are not conserved quantities in this problem because if you think of the bat as a system, there are external forces being applied to it. The baseball colliding with the baseball bat and the reaction force here as the bat butts up against my hand. So then therefore I'm going to set up a change in momentum and a change in angular momentum expression for the baseball bat in this example. Here's how we're going to approach, first of all, the linear momentum. The total amount of force that's exerted upon the baseball bat is going to be F minus R. This then results in a change in the momentum of the center of mass of the baseball bat with respect to time. Like so. So after the collision occurs, for example, the baseball bat will begin moving in this direction with a VCM. Okay, now I'm actually going to take the time interval here and move it up to the left-hand side. We'll describe this actually as an impulse example. Remember that force multiplied by time is equal to impulse. That's over here on the left-hand side of the expression. And then on the right-hand side of the expression, we have the change in the momentum of the center of mass of the baseball bat. So then therefore, let's just simply write the right-hand side of the expression as mVCM and then minus 0 because the baseball bat begins at rest. We are, by the way, not taking into account what happens if you take the baseball bat and swing it into the baseball. We'll just have the baseball bat just sitting there for simplicity in the example, that is initially. Okay, now let me go ahead and write out a torque equals change in angular momentum with respect to time expression. Okay, so I'm going to write this as tau external equals delta L divided by delta T, like so. So how do I describe the external torque? Well, the external torque is going to be an R cross F for each of the forces that are present here in this problem, where we have the pivot point right here. Now, is there a torque exerted on the bat due to the reaction force? No, and the reason why is because there's no moment arm for R cross F for the reaction force. The reaction force itself is applied at the pivot. But we will have a torque exerted on the baseball bat due to the force F. So for the force F, right here is the moment arm. That right there is the unknown distance x, like so. And then right here is that force vector that the baseball exerts upon the baseball bat. Right angle between the two. Okay, let's do R cross F. When you do R cross F, you end up with a torque vector out of the board. This then ultimately means that there will be an angular acceleration for the baseball bat like this. In other words, the baseball bat will start to rotate counterclockwise in terms of our diagram. But right now, we have a torque vector that comes out of the board like so. So right here is that torque vector. This is our external torque, and magnitude is just equal to x times F. Like so. Okay, now in the next step, as I just erased a moment ago, let me go ahead and take the delta T here and move it to the other side. Like so. This quantity over here, basically torque multiplied by time, is sometimes referred to as angular impulse. And this then equals the change in the angular momentum of the bat. Okay, now the final angular momentum of the bat is going to be an I omega, like so, minus the initial angular momentum, which is equal to 0. And now let's go ahead and rewrite the right-hand side of the expression in the following way. So let me do some erasing. Let's write, first of all, the rotational inertia I of the baseball bat when it's being pivoted about this point. This is 1/3 ml squared. Okay, and then multiplied by the omega. How do you describe the omega of the bat, for example, as it begins to rotate like so? Well, we'll do so in terms of VCM, where the distance that the center of mass is from the pivot is 1/2 the length of the baseball bat. So we have V equals R omega. So omega is equal to V over R, where the R is L over 2. Like so. Okay, let's go ahead and simplify that expression a little bit. I'll do so by moving the 2 up here. I'll cancel an L like so. And I get to this expression here, and now you say, okay, well, what do we do now? Well, I've got this expression here essentially describing the rotation, and then this expression here describing the translation of the bat after the collision. So now what I want to do in the top expression is let the reaction force R go to 0. So now let's set the reaction force equal to 0. If I set the reaction force equal to 0 in the top expression, I now get an equation for F delta T, which is this quantity right here. And now I'll take that expression for F delta T and plug it in here. When I do, the only unknown will be X, and I'll get an answer for X in terms of L. Okay, so let's go ahead and finish the example. So let's plug in from the top board, like so. Notice that the M VCM, there's an L here as well. The M VCM cancels here and here like so, and now we have our answer. X is equal to 2/3 L. Now, a baseball bat is not quite a uniform stick. So 2/3 of the length of the baseball bat is roughly here, but it's a little bit closer to this position here when you're talking about the sweet spot then of a baseball bat. Depending upon the shape of the stick and depending upon how the mass is distributed, we have more mass to the stick over here at this end of the stick. This then moves the sweet spot further and further away from the pivot point. So this is why, for example, with a tennis racket, you have the sweet spot that's basically in the middle of the netting on the opposite side of the racket from where you're holding it. And in particular, a golf club, basically the sweet spot is in the middle of the club head, which is way at the other end of the stick that you're holding onto. And the reason for that is because most of the mass of the golf club, particularly if you're talking about like a 1-wood or a 3-wood, is basically at the location of the club head itself, okay? All right, so that's the sweet spot problem. That's for you sports fans. I'll go ahead and conclude this video here before we move on to the next examples.